everyone, we're going to get started now. Happy Halloween. Also, today is week 8, lecture 2. Oh, and I haven't shared my screen. Okay, here we go. That's better. All right, hello again. We're going to look at deletion today. So we're going to do a bit of a recap on linked lists. Then we're going to, we haven't done any deletion yet. We'll do a little bit more insertion as well. So today there's a revision. Tomorrow I'm going well today so far. Tomorrow there's a revision session 2 to 4 online. So I think there's still spaces. If there are not still spaces and you're interested in going, just let us know. We can probably make more spaces for you. Okay. All right, so today's lecture, we're just going to recap traversing a linked list, searching for a value, inserting in the middle. We're going to look at code to insert at a particular position, and then we're going to start looking at deletion. Shh, everyone be quiet. There's a link to the week 8 live code as always. So let's just get started. Actually, before we get started, how's everyone going with linked lists? Great. Okay, yeah, a lot of sort of wavy hands. It does take a bit of practice to get on top of them. So this is the last topic for the course. So we do have some time to spend on them, and you'll have time to practice it. And also the assignment has linked lists. So you're going to have lots of chances to practice and get your head around them. Yep.
This is the last topic. What are the future labs about? The future assignments and labs?
Well, the assignment's about linked lists.
Yeah, and then next week's also linked list.
Oh, right. Like in terms of lectures, we'll be doing, Monday will be linked lists. Then we'll start talking about the exam and doing some revision. Okay. And in labs, there'll be linked lists. And actually, in the last week, in labs in week 10, we'll give you a practice exam to do in the lab. Okay. It's not marked like an exam. It's just for lab marks. And just by having a reasonable attempt at it, you'll get the marks for the lab. Okay. So yeah, finishing up linked lists, revising linked lists, revising everything, talking about the exam. That's what's coming up. Okay. But yeah, how does everyone feel about traversing a linked list? We'll just go over it anyway. So remember, this is what we can visualize our linked list to look like. If we want to go and visit every node, so for example, we want to print every node in the list. We want to count every node in the list to see how many nodes we have in the list. We do a traversal. We start at the beginning and we go through every node. Now, typically to do that, what do? Well, we don't want to lose the variable that's keeping track of the head of the list or the first node of the list. We typically make another variable. Oops. We don't have to call it current, but we often do, or car, or something like that. And to move it along to the next node, what do? Everybody? Anybody? Everybody? How do I move this current, which is pointing to the first node, to the next node? Yeah, current equals current next. So I'd do something like, this, current equals current next. And that's moving our pointer along to the next node in the list. Okay? Does anyone have any questions about that? That's really important to know that. Then we can keep going. When would we want to stop if we wanted to visit every node?
No.
When, current is equal to null. Okay? That's if we want to go through the whole list. All right. So we're going to write a function to search for a value in a linked list. And we want to return 1 if it exists and 0 if it doesn't. So who thinks they'd know how to write this? We're just doing ints with this one too. Okay. So let's just have a go to just get our brains back into linked lists. Well, right now, what have I got? Oh, I might need to increase that size a bit. Get my mouse. All right, I've got code right now that's just basically creating a list for me using functions that we've already written before. Let's turn like this. So right now, all it's doing is creating a list, and it's got 4 values in it. So we're going to write something to search for something in a list. Let's create a prototype. We're returning 0 or 1. So we're just going to, our return type's an int. And I'm going to call it, I don't know, list search. And of course, we need to pass in the actual list and maybe what we're searching for. What value are we looking for in this list? Okay, so that's our prototype. And we're going to write this code. We need to think about test cases as well. But when we write this code, what's our approach going to be? What are we going to do? So let's even just go back to the slides so you don't have to look at my bad drawings. I'll go the right way. So we could do an approach like this. We can start at the beginning, but as we move along, we're just going to check. What are we going to check? Yeah, is the data inside the current node, is that equal to what we're looking for? And then if it is, what do we do? Yeah, we can stop looking. That's right, we can stop looking, we can return 1. Or we can stop our loop, and then return 1, however we want to do it. If it's not, we keep looking, right? And we go to the next one, we check that. We check the data inside that. And eventually, what will happen? What are the 2 ways our loop will end? So the 2 things can happen is that we find it. So our loop will end when we find the thing we're looking for, or we won't find it. Imagine we're looking for 99 in this list. We're going to keep going. Eventually, we get to null, right? And we know, oh, we didn't find it. Okay, otherwise, we would have found it and stopped the loop before that. So there's a few different ways you can write this. But most of them are going to involve, well, I think we need some kind of pointer that starts at the head and keeps moving along. And we need to make sure it's not going to go past the end of the list. And we need to make sure we're moving it along. So this is sort of the basis for a lot of the code that you're going to write. But we can do it 2 ways. We can check it in here and say, well, if current arrow data, so if the one that we're currently up to, if the data inside that is equal to what we're looking for, then we've actually found it, right? So we could return 1 in here. Does that make sense? And then what will returning 1 do in the middle of a function? Yeah.
True. Oh,
sorry, yeah?
Return true.
Yeah, that we're using that to return true, but that will end the whole function if we put a return in there. If we haven't found it, we're going to keep searching, searching, searching. So if we get down to here, what are we going to return? Yeah, if we get to here, we know we didn't find it, and we return 0. Okay, so that we could do it like that. We could also have a condition in the while loop checking for the data equal to the value in there. All right, let's try it like this. Now, what are the kind of cases we want to test? Oh, test an empty list, yes. What else do we want to test? So with something like this, we might just,
One in the list.
yeah, if there's one in the list. Anything else we can think of? What are the cases in terms of the data we're searching for? Often in these cases, we want to make sure we test one that isn't in the list. Right? Test what happens if we're trying to find 99. Is it going to say, no, I didn't find it? Sometimes we want to make sure we test something that's the first in the list. Does it work if it was the first one in the list? Does it work if it's the last one in the list? Does it work if it's between two nodes, like it's not the first or last? So often we want to test all these different cases. So let's start with an empty list. Let's just do it up here. List search. I'm going to pass in the head. Why have I called this head 3? Just do that. All right. So let's just, it doesn't matter what we search for in this empty list, right? But, yep.
Do we need to test if it's a valid data type or not?
No, we're not going to test that. We can assume in this case we're given an int because we're not really doing any input checking or anything like that. So in this case, all we're really checking is does our code crash with an empty list? That often happens. Does it return no, I didn't find it? I'll just do something like this. If found like equals 1, print found. Actually, I'll search for 99. I'll always just search for 99. So I know if we find it, we've done something wrong. Okay, so we can try and compile this. If it crashes or it prints that it found 99, we know something's very wrong. No, it didn't. All right. We can keep doing this for other cases. So we've done our empty list. I could just search here now and check if I can find that value 13. All right, we should be able to find it. Yep, found 13. Again, let's test if something's not in the list, such as 99, but once we've got all these values in the list. Yeah, it's not finding 99, which is good. Let's test if it can find the first node in the list. What's the first one in our list is 13. So we want to make sure it can find it if it's the first one in the list. If it's the last one in the list, that should be 5. So we should find 13 and 5 if we search for them. And I don't know, either 42 or 17, which is somewhere in the middle. So these are the types of things you have to consider, both when you're writing your code and when you're testing it. Okay. So this isn't the greatest way to test stuff, but we don't have a lot of time to set it up. So I was able to find 13, which was at the beginning, 5, which was at the end, 42, which was something in the middle. It's a small list. I could really test every single value that's in there, but often you don't have that sort of, you might not know in advance. All right, so we can sort of be reasonably confident this kind of works. Does anyone have any questions about that? Any of these basics here? All right. Yeah?
I wonder, what if we don't want it to be found based on like the value, but its placement in the list? And like so far we've only been able to find like the middle.
Yeah, so that's a really good question. What if we want to find it based on its location in the list? And that's actually what we're going to do next. So we're going to take the code, we're going to look back at what we did for find in the middle. But if we can work out the index of the middle element, or the position of the middle element and find that, There's no reason why we can't go and find it at any other position, because it's going to be the same logic. Okay?
Oh, yeah.
Yeah. So we're finding that position, I guess, and inserting, but you could adapt the code to just find the element at that position. All right, so let's have a look at that. So yeah, we did this. We inserted in the middle of the list. And the first step in doing that was basically finding the middle of the list. And in fact, we wanted to stop one node before where the middle would be if we inserted the new element. So we wrote code to find the length of the list, and that was just a traversal that had a counter. Let me just remind you. List length. Gosh, what have I got there? Yeah, this was just a traversal, right? A traversal, we start at the beginning. I've written current instead of current, same thing. But we've got this counter, a counter counting up each time we see a node, right? That's going to tell us how many nodes there are on the list. So if we're searching for something at a particular position or trying to insert something at a particular position, we can also use a counter. So when we did this to insert in the middle, we first called our list size function to find out how many nodes there were. We divided it by 2, which meant, and the way I described positions, I said that's 0 position, that's 1, etc. So we want to insert something in the middle. We want it to go here. So that would end up being at position 2. This would end up being at position 3, position 4. All right. So yeah, this is the position list size, which is 4 divided by 2. So we're going to do a loop, and we want our current to stop just 1 before that position. So we wanted our current to stop here. Okay? Because then we can connect this node, and it's now in the middle of the list. All right. So yeah, we had a loop. We set up our traversal by having a head, and we set up our counter as well to be 0, and we've got the current node here, and we're at 0. Every time we go through the loop once, we go to the next node and we increment our counter. Now in this case, we stopped here when our counter was, it got to 1. We stopped because this is where we want to start inserting our new node. And we created our new node, and we wanted to link it up. So we have to link it up. So this points to this, and then this no longer points to here, but to here. So just keep in mind, if this is new node, right? We've got a variable called new node that has the address of this node. We've got a variable current that has the address of this node. How do we refer to this node? How do we know where this node is? Yeah, current next is what has the address of this node here. So we can call this current, we can call this current next, and we can call this new node. So we want to know what to set this next value in new node to. We want to hook it up to this node here, which we've called current next. So we say new node next equals current next. And again, you know, what we're actually doing is copying this value from here to here, which refers to this node. But what you really want to be thinking about is the next node after new node should be what was currently the next node after the current node. Yeah. So you want to read it like new node next equals current next. This is new node. The next one is current next. This was current next. So we do that little connection. Then we do this connection from here. Current next, or the next node after the current node should be this new node. So that's what we've done there, and we've connected it up. We've inserted it in the middle. Okay. And we've got all the code that does that. All right. So let's have a look at that code again. We added a special condition because things were crashing. If we tried to insert in the middle of a list that was empty, it crashed. So we have a special case. If the list was empty to begin with and you're trying to insert in the middle, this is going to be the only node. Let's just return that node. Other than that, we're doing exactly what we just said in the slides. Now, we want to adapt this code, or we don't have to. We could start from nothing, but we can adapt this code to just insert at any given position. So I could say insert at position 0, it should end up being the first node in the list. Insert at position 3, it should end up being basically the 4th node in the list, right? Because I'm counting from 0. Now, instead of always we don't have to calculate the middle anymore. Instead of going to the middle, we're going to whatever position the person using this function wanted. So this code is nearly going to work as it is. We still use a counter to count along until we get to the relevant position. This time it's not the middle, it's just whatever the person said. But there might be a few cases that don't work, because when we were just limiting it to the middle, we were never trying to insert right at the end maybe. Maybe we were never trying to insert right at the beginning unless our list was empty. There might be some things that worked because it was a little bit more limited. You might already have ideas about what they might be, but let's just test it. Okay. Oops. And we're going to need to test some of the similar things that we did before. Insert at position. Okay, so I've just got something to print out so we know what we're doing. And I'm creating a new list with nothing in it. Okay, and we're going to start trying to insert at different positions. Now, the first thing we're going to do is just try, does this work if we're inserting into a linked list that's empty? What do I want to put in this list? It doesn't really matter. What position? It doesn't really matter, I guess. Does this crash? Or even let's put naught, do something sensible. Now, it would be good if I then printed the list after I tried to add something to see if it works. Okay, so ignore all this stuff above. In fact, I'll put a new line here to make it easy to ignore it. I just didn't want to delete the stuff we did the other day. Okay, insert at position when there's nothing in the list. That seems to work. It didn't crash, it's inserted it. All right, now that we've got a size 1 list, can we insert now at position 0? Let's check it out. So I want the value 7 to be inserted into this list at position 0. So it should end up at the start, right? Just going to move this. Oh, it doesn't. That's not exactly what we wanted, was it? It's supposed to end up at position 0. So obviously this wasn't, maybe not a situation in the other one, or maybe it was wrong in the other one too, but we weren't asking for an exact position in the last one. So this doesn't work, but it didn't crash. Let's just see what else does or doesn't work. I've got 2 nodes now. Let's see if I can insert at position 1. So it should end up in the middle. Okay, so that's working. Not working to remind me. What about inserting at the end? Now in this situation, what would the position be at the end that we're looking for? Well, yes, 7 is at position 2, but if we do it there, let's just try it. I think it'll be at position 2, so it'll come before the 7. And that's kind of what it's supposed to do. Let's make this, I don't know, 19. Yeah, so that's what it's supposed to do. So if we wanted to insert it at the end, 0, 1, 2, 3, it'd now be position 4. I'll move that here. It'd now be position 4 that we want. Let's make it 21. Is this going to work? It is. Now, what about if somebody types in 99? Like, let's put it at position 99, or a position that doesn't yet exist. Position 1000. What do we think is going to happen?
Crash.
Yeah, it's going to crash. All right. So we've got to work out what we want to do in this situation. Now, if we wanted to just add it to the end of our list, right? If it's too big, let's just add it to the end. If it's too small, like -5, let's add it to the beginning. We can program that in. How would we fix our code to do that? So let's have a look here. What line's crashing? I'm saying it says current equals current next, and it's saying current is null. So what's wrong with this loop?
Let's check the position first. If position is past the size of...
Well, we could check the position and work out the size of the list. That's one way. Or what's the other way? Yep. Yeah, I could check if car is equal to null, or one better, if I want to insert something at the end, what node do I need to stop at? Yeah, I need to stop at the last node. I don't want to go past it. Yeah, I know you said that. And that's exactly what you said, so that was right. But I just was trying to say what people might be thinking. Yeah, we could do something like this. Okay, this will make sure we at most go to that last node, so we can always at least insert it at the end. Okay, is this going to work? Did it work? I've lost track of what we're doing. Well, it didn't crash, we know that. So, that looks weird, doesn't it?
Still doesn't work for the one.
So hang on, didn't our 3 end up here? Yep.
In the other one, in the while it did say not equal to null.
Okay. Oh, I typed it in wrong. Thank you. You deserve lots of chocolates. I got my condition backwards. I don't know why. Okay, there we go. So now that part's working. We've still got the thing where it didn't insert it right at the front though. Let's just see what else is making things crash. So you're going to be doing all this sort of stuff by accident, right? When you're coding, things are going to be crashing. I've already tried inserting at the beginning and it didn't work. So let's get this working. So when we're trying to insert at position 0, it was ending up at position 1. So we want to go and fix that. Now, what can we do here? So here we've got a special case for if the list is already null, we just return the new node. If we want to insert at position 0, yeah?
We check if the counter is like at 0 specifically.
Yeah, we check if it's at 0 specifically, that's right. And then we've sort of got the same case as what we've seen before when we inserted the node at the beginning of the list. So we might be able to say something like this if, oh, I'm looking at the wrong code. Oh my goodness. Okay. Or pos equals 0, right? But we need to add something else. We need to say new node. So if I'm, just a reminder, if I've got stuff in my list already, okay, I've got my new node here. I've got head here. I don't just want to say head's my new node, right? Because then, yeah, I've got to set this connection. So I've got to say new node next equals head. And that's going to be fine. Even if head is null, it's fine to say new node next equals null. So that should now, I think, work for all of these cases, I hope. So we should see that 7 as the first one in the list. Okay. Now, one more thing we could change though is to just say, actually, if somebody types in something like -100, let's just put it at the beginning of the list as well. So that's something you might want to go and test later. Now, if you just wanted to find something at a specific index, you'd do something less complicated than this, right? You could just do the loop part and not worry about all the different edge cases and inserting things. All right. Any questions about that? So this is complicated code, right? So it might take you a while before you're able to write this code yourself or even completely understand it, all of it. Okay. What's next? Deletion. Who wants to keep going with deletion? Yeah, we're going to. We'll do a bit of deletion, then we'll have a break. We'll come back. We'll probably do a Kahoot just to give our minds a break and then keep going with deletion. All right. I'll give you a few seconds to let your brain rest or talk. Okay, we're going to start. So let's look at deletion. Now, in all of these examples, we're assuming we're deleting it and we're freeing it. There might be other scenarios where you don't want to delete it, you want to save the node and do something else with it, but we're deleting it and freeing it. So let's start up considering one of those, always tricky little test cases of what if the list is empty. So you should always be thinking of that for every function you write. So before we've made our program crash, let's try and think about it. So if the head's null and we're trying to delete something from it, we can't. If there's nothing in the list, we can't delete anything, no matter where we're trying to delete it from. So if the head of our list is null, we can just return head or null. That's what our list is. Okay, other than that, imagine we do have some nodes in the list. Here, we're not searching for anything. we're doing the simplest case, let's just delete the first node. Now, there's a few things you might try and do, because what we want to do, we want two things to happen here. We want the head of the list to be this node here, right? Because we want to get rid of this one. So we need to write code that will make this the head of the list and also free this. So often the first thing people might do is call free. Let's call free on this head of the list. What's the problem now? Yeah, we can't access the rest of the list. So we don't have any variable that's keeping track of this node here. Whoops. We don't have any variable that's keeping track of this at all. The only thing that had this address or knew where this node was this node here, and we've just freed it. So if we do that, and then we try and say, okay, well, head now equals head next, this will crash our code. The DCC will print out for us, you've used a free after a malloc. I mean, you've tried to access freed memory or something like that. And it will crash. So we don't want to do that. Let's try it to see. Let me go to this code now. Delete first. Here it's easy. When we test it, I'm just going to keep calling delete a bunch of times. Okay. So yeah, if I just say free head, and then head equals head next, return head, what happens? Well, actually, DCC is trying to warn us, pointer head used after free. But if we try and ignore DCC, yeah, then we get a runtime error saying you've used something you've malloced after you've freed it. So this is obviously not the way to do it. Okay, now the other thing you might do is say, okay, well, I'll do it the other way around first. I'm going to say head equals head next. Now what's the problem? Yeah, I've lost the head of the list. So there's different ways to do it, but we need some other variable holding onto one of these nodes, right? So yeah, we can no longer free this. So actually, this would work in terms of our list would be connected up fine, but we'd have a memory leak. So one way to do it is just have another variable pointing to at least one of these nodes. I'm going to point to this one here, because then I can move this one on to the appropriate thing and then free this one. Okay, so just be very careful when we're working with deletion and free and linked lists in general. If you don't do things in the right order, you lose things or break things. So let's try this. So I'm going to, let me just delete all of this. Struct node, I'm just going to call it temp equals head, right? Then what am I doing? Now I can move head. So I can say head equals head next, but now I've still got a pointer to that original node, so I can free it, right? So I've said head equals head next, and now I can free this node. And then I can return head, right? So then the main function will know where the head of the list is. Let's compile it. Now, let's have a look at what my code is doing when it tests it. I've got a list. I've created a list with 10 elements in it, and then I'm going through and deleting all of them, and I'm even deleting an extra time just to make sure I'm trying to delete from an empty list. So this is going to cover all the sort of possible test cases here. And I'm printing them out each time. Oops, what have I done here? What did I forget to add in? So let's go down here. So here it's saying this, I'm accessing a null pointer. Why would I be accessing a null pointer here when I'm accessing head? When would that happen? If the list is empty. So remember on my slide, the first thing I did was said you need this special case for if the list is empty. But I didn't put it in there, but I tested it and then, oh, that's right, we've got to check. No, I didn't do that on purpose. I meant to type it in. I'll be honest. Okay, so again, just check things work for that case where you've got an empty list. Okay, so now we were able to delete the first element one by one by one by one by one and end up with nothing. Now, how do we know if we've freed everything properly and we don't have memory leaks? We can, has anyone used this yet? Compile with DCC leak check, like that. Then when we run it, it doesn't say anything because we've freed all the memory. If we go and look in this code here, we're going to have memory leaks because I haven't freed anything. We've made lots of nodes. We've made 5 lists. What have I done? I've forgotten to put -O. All right, so this is what you'll get if you do have memory leaks. So here I haven't attempted, I've said, yeah, we're going to have memory leaks. You're going to end up with a printout saying you've got a malloc online, whatever, and you haven't freed it. And you could have many memory leaks, and until you fix all of them, you're going to get an error message like this. Now, because we ran it like this and we didn't get that message, we know that we did actually free all the memory in that list properly. Okay. Any questions about that? Okay, so, yep.
Why do we check for memory leaks?
Why do we check for memory leaks is the question. So in a lot of our programs, if we have memory leaks and we're just making a couple of linked lists that aren't very big, it's not going to be an issue. But we want you to get into the habit of knowing how to free memory and being precise with it and being able to free for every malloc. Because if you've got a program that's running for hours or days and you're gradually leaking memory, eventually you're going to run out of memory and you might have to stop that program, shut down whatever it is, or your customers have to keep restarting their computer or restarting their game or whatever. That's why. So we want to make sure that you know how to do it precisely and have a free for every malloc. Also, even in this course, there might be situations where you could put a malloc in a loop and not free it and just accidentally have memory leaks like that. So we just want you to make sure you know what you're doing with it and being precise with it for when it does matter. But yeah, you could get away with your program still working in this course without doing it, but that's why we have that tool. Yep. Yep, question?
So for the null case, do we have to return head or do we return null?
It doesn't matter because if head is equal to null, it's just going to be null. It's going to be null either way. Yeah. So I probably did it one way on the slide and the other way in the code, but that's because head is null in this particular situation. All right. Yep.
Code, how come you had to change head to head next? Was that in
Well, so we're trying to delete the first node. So right now, head is pointing to the first node, right? We don't want it to. We want that first node gone. So we say head equals head next. So now this node here is going to be the first node in the list. Now this is basically the list here. And then we free that node and that node's gone. So now we've deleted that first node. Yeah. Yep.
Just a clarification, if you want to delete the nth node, we just have it have a while loop that ends when it's equal to the whatever position you want it to.
Yeah, so the question is, what about if we want to delete it not at the beginning? Do we have a loop that goes through and finds where we want to delete it?
But it's actually kind of the same code to find a node, right?
It's similar. It's similar to, yeah, inserting at a particular node. You've got to find, but we're going to do more cases. We're not just going to leave it at deleting the first node, but you'd have a loop and you'd go along to that position. Make sure you've got a pointer to the one before it, etc. But we're going to go through that after the break. So let's have a break. We'll come back at about 5 past. There are chocolates and lollies down the front if you want some as well. Just take them. There should be enough for everybody, as long as you don't take the whole bucket. So we'll come back at about 5 past. Hang on. So let's continue with some deletion, a little bit of deletion, then we'll do a Kahoot. So yeah, we've learned how to delete the first node. So sometimes you might just want to delete the first node. But even in situations where you don't actually want to delete anything, at the end of your program, you're meant to free all your memory. So we always need to write a function that will just go through and delete all the nodes, free all the memory. And there's going to be the similar issues to what we saw with deleting one node. The issues will be, you can't free something and then try and access the pointer and all that sort of stuff. So let's have a look. Now, this code here is sort of on the right track. What's wrong with this? So this is kind of just like a traversal, right? We've got current equals head while current is not equal to null, which makes sense because we want to delete every single node. We don't want to leave the last node hanging around. Yeah. So can everybody see that if I free current, so I'm freeing a chunk of memory, and then I'm asking, well, what's your next field? We can't do that. So that would crash. But this is the right idea of what we want to do. We just want to go through every single node in the list and free every single one of them. We don't need a list at the end. We're destroying the whole list. But we don't want it to crash. So yeah, accessing this, which has just been freed, is what we can't do. So again, we're going to need to use a second variable or something to keep track of the one thing so we can free the other thing, etc. So there's a few different ways you could do it. Now in this case, to me, this is what makes sense, but you'll see it in different ways. And also, by the way, I'm just starting to have the lists drawn in a sort of way that will be similar to how you're probably going to draw them yourself as you're working through stuff. So hands up who draws their lists as they're doing their code. It really helps. And do you draw fake addresses or do you just draw boxes and arrows? Yeah, okay, good. So at the beginning, it's helpful to show those fake addresses to understand what's really going on. But at some point, it's too much. It doesn't even matter what these values are. Okay. All right, is everyone ready? So, yeah, I've got a current. And I've also got the head of my list. So I've already got two variables. And the head of my list is changing anyway, and we're destroying the whole list. So I can just use the head variable, or I could create another one. But basically, I'm just saying, okay, let's move head along. Head equals head next. So I'm saying, let's move head along to the next one. Then I can free current. Yep, I've moved head along. Then I can free current. And then I can say, okay, current equals head. And I can do that again. I say, head equals head next. Free current. And current equals head. Head equals head next. I can free current. Current equals head. And now my loop will stop. So that should take care of not losing any of the links, but not using things after we've freed it. Now you might do it slightly different. You might create another pointer called temp or whatever you like. You just got to make sure you have all those elements. So let's just check that that works. Delete all. Okay. So it's almost like a traversal. Well, it is. Oh. Okay, but Oh no, well, we're not really doing that now, are we? We're saying, let's move head to the next one. Then we can free the current one. And then we can move current along to the head. Yep. All right. So if instead of deleting all of these nodes one by calling our delete first function, instead of doing that, I'm just going to call delete all. And then I'm going to check for memory leaks. Yeah. It didn't print out that message saying you didn't free something after your malloc. Okay. All right. Any questions about that? So that's delete all. All right. I think what we'll do, we do have one more piece of deletion code to look at. We're going to search and delete. So we're going to search for a particular value. So we wrote code to search for a particular value before in a list, but we want to delete that value when we see it. Okay, and we've got to test for all the different cases. What if the list doesn't contain that value? What if it's the first one we're deleting? What if it's the last one we're deleting? What if it's somewhere in the middle? Then the other thing is, what if there's more than one? What if we want to delete the value 1 and there's lots of them? Our first one, we'll just assume we're deleting the first one we find. We're not going to delete all of them. But then we'll move on and consider that. All right. Let's do the first version of this. So, now, if I want to delete a node, I actually need a link to the node before it. Because just say I want to delete node 42 in this example. I want to get rid of this node, but I need to connect the one before it to the one after it. So if I just traverse through here and find this node, it's not going to help me do it if I don't know what the previous node was. I'm then going to go back through it again and find the one before it. So I want to think of this as I write the code. So I want to find the previous one. I also need to know that that one actually has the value I'm looking for. Then I can reconnect it and free it. So there's two kind of main ways people do this kind of thing. My favorite way, I've got a favorite, sorry?
You can use current next data.
Yeah, so one way is to look at current next, okay? That's one way, instead of looking at the data in the current. The other way is to have a previous, keep track of the previous one as well. So I'll show you both ways actually. You're lucky we'll do this one twice, everybody. The first one I'm going to do with a previous pointer. So this is like we've got current and we've got previous. And previous, it's like it's trying to follow current along, but it's always sort of one behind it and it's sort of chasing after it. But this is how we can do it. We set, right at the beginning, when we set current to head, we set previous to null. Then as we're going through the list, now in this case, in my condition, my loop is stopping if we get to the end, which is null. It's also stopping when I find the thing I'm searching for. Okay, so it's either going to stop when I find, 42, for example, or it's going to stop if I was looking for something that's not in there. But each time I just say previous equals current. So previous comes along trying to, chase after current, and then current moves to current next. So yeah, previous equals current, current equals current next. And we just keep doing this. And we're looking, is this what we're looking for in current? Is current data equal to, let's imagine 42? No. Are we at null? No. So we move previous to point to current, and we move current to point to current next. Now here we say, is current equal to null? No. Is current data equal to 42? Yes. So our loop is going to stop here, but we've got this pointer to the previous node. So this gives us everything we need to be able to delete this node. So what do we want to do? Well, we want to somehow make this connect to here and then free this. And we've already got two pointers, like we've got a previous and a current. So we shouldn't need to make an extra temporary variable or anything like that. We should be able to just say, well, what would we say to do this? Yes, so this one here, I want previous next. I want the next one after previous to be this one here, right? What do we call this one? Well, yeah, this is current next. So I want to set previous next to current next. So that's what I do for that. And that's setting this link from here to here. Is everyone happy with that, this line of code? Now what do I want to do with current? I just want to free it. Yep, and I can because I've got pointers to everything else. I'm not going to lose anything. And if all I'm doing is just deleting once, then I'm done. I'm just going to return the head of my list and I can finish. It doesn't even matter where previous and car are anymore. I'm done. So that's how I can do it with this approach. Now, again, we probably need to worry, yep.
If we free current, would we still have current next?
Well, now we can't say current next.
Okay.
So if we'd freed it, if we freed current and then said previous next equals current next, we can't do that. But if we've done that first, before we'd freed it, we got that information from it, and then we're basically destroying it, that's okay. So again, we've got to do it in the right order. And there might be other conditions that we need to think of, right? Like, yeah?
Yeah, like if we didn't find 42, then the current will be null. Like
That's right. If we get, so one observation is, if we don't find it, imagine we're looking for 99, we don't find it, we're going to get to the end and finish our loop and current's going to be equal to null. So we're going to need to make sure that if we get to the end of the loop and current's equal to null, that means we didn't find it. We've got to make sure we're not trying to delete something. Okay, so if we get to the end, current's equal to null, we don't want to do anything. Does that make sense? If current's not equal to null, we found something in the list we want to delete. What's the other situation that might arise? So what are the typical things we think of? Is this going to work if we're at the end? Is this going to work if we don't find it? What else would we think about? Where else could we be deleting it from? Yeah, the beginning. Is this going to work if we delete it from the beginning? So if we're deleting it from the beginning, we're going to be in this state with current is equal, pointing to the node we want to delete. And what's previous going to be equal to? Oh, no, haven't gone back far enough. This state here, this state here. When we first start up, if it's the first node, previous is going to be equal to null. Now, is that going to be a problem? It's going to be a problem if, let me just get rid of this. Ignore what you see here. If I've got current is here because we were looking for 13 and previous is null, doing this, we're dereferencing a null pointer. Okay, so we're going to have to do all these checks. So let's just try and write this up. Okay, search and delete. So we've got our previous node set up and our current node. And we've got our condition while current is not equal to null. And also, we're stopping if we find the piece of data that we're interested in. So we keep going when it's not equal to that value that we're looking for. Yeah? So this is either going to stop when we got to the end and we didn't find it, or when we find the piece of data we want to delete. And at each point, what are we saying? We're moving previous along to current, but then we're moving current to the next one. So that's the behavior that we saw in the slides, moving them both along. Now, when we get to here, what could be the case? Now, the first case you brought up was, what if current is equal to null? If current is equal to null, current, what do we want to do? We didn't find it. We didn't have anything to do. We don't want to delete anything. So we don't really want to do anything. We want to leave the list exactly as it is. So we could either return head now, or we could wrap all of the rest of our code in if current is not equal to null. And it depends what you like better. I like using return statements, but some people don't like you to use too many. Yep.
Wouldn't it need to be previous next in your while loop?
Here, well, what we're doing is we're always just moving previous along to where current just was. So here, previous is equal to null at the beginning. So if now we said previous equals previous next, in this situation, it'd crash. So what we do is we just say previous equals current. So it moves it along to where current is. And then we say current equals current next. Now previous next would work. We could say previous equals previous next. But just right at the beginning, because it's equal to null, we can't do it like that. But yeah.
Mom, how about we wrote some like the previous and the current with head? That way, like when the first item which we are searching is in the first node, even if we delete it, the previous will still have it.
I think, I'm not sure exactly what you just said.
Like instead of starting with null, we could start the previous with head.
Well, if we start the previous with head, and then we could update it at the end of the loop. There's different ways we could do it that probably would be the same. So code it up and try it. It's probably the same logic, but doing it at the end of the loop, that might work. Okay. All right, so if current is not equal, if current's equal to null, we don't want to do anything. We're just going to return head. If it's not equal to null, well, the main thing that we wanted to do, let's go back and remind ourselves, is previous next equals current next. We'd found current, we wanted to connect previous next to current next. So previous next equals current next. Previous. And then what did we want to do? We wanted to free current, because that's the whole kind of point. We want to free it. And we've connected everything up around it. So we'd free current. Now, as we've already sort of suspected, this is going to be a problem if previous is null. So if previous is null, we don't want to do this. Oops, that we don't want to do this. Maybe this is what you were saying. What do we want to do? So if we're at the beginning, let me go back. Previous is null. How do I want to delete this? How do I delete this? So I'm trying to get rid of this.
Previous is what's required next.
Well, yeah, I want to make sure, because I'm not just deleting and destroying my whole list. I need to make sure my list is a proper list and everything's joined up. So this is now the head of the list. So this is very important this time that I do connect head to what's now the head of the list. And then I can free current, right? And because we're not doing anything else, we're stopping. We don't have to worry about where current will be later, but we need the head to be in the right spot. So let's try that. So we've got, what did I just say? Head equals head next. So this is the part where we're connecting it up. If it's at the beginning, previous is null, we're just changing the head of the list. If it's halfway through the list, or even at the end of the list, we need the previous node and we're connecting it to current next. As long as current's not null, because if current was null, we didn't find anything to delete. And down here, we're freeing current. Yep.
Is there a difference between setting head to head next or head to current next?
No, not in this situation, because they're pointing to the same thing. So I could say, yeah, head equals head next or head equals current next right now. And after I free current, I could do none of those things, yeah. So yeah, do it in the right order. Is this going to work for everything? I don't know. Linked list deletion. Oh, I've got to actually use this to see if it works. Okay. So let's test all these cases. Head equals search and delete. So let's try the first node and then we'll print it. Maybe let's just try them one by one to see if they work. Oops. Yeah, that seemed to work. Deleting the first node seemed to work. Let's try deleting the last node. That seemed to work. Let's try deleting one in the middle. 5. Oops. I don't mean exactly the middle. I just mean somewhere between two nodes, not the first or the last. Yep, 5's gone. Let's try and delete something that doesn't exist. 99. It did nothing. Would it crash if we just gave it an empty list? Oh, let me do it. I could just pass in null actually, but I won't. Let's just do it up here. I'll just stick it up here. Oh. We're just checking if it's going to crash. No, it doesn't. So it seems to work. Is there anything I've forgotten to check? All right. And at the end, we're deleting all. Now, if we've done something silly in our search and delete, if we'd forgotten to freeze something, we would end up with a memory leak here. Because delete all can't come back and free things that we've already disconnected from the list. Yeah, but we don't seem to have any memory leaks. So I think that's good. All right, so that's search and delete version 1. Now, before we do version 2, let's just have a little bit of a break. Let's do a Kahoot. It's a linked list Kahoot. And we'll come back and then do the second version, which is going to be quite similar. All right. Oh, I haven't logged in. Right, we've got Halloween prizes. They're not very exciting. I don't want you to be disappointed, so I'm letting you know that in advance. Okay. Okay, so I'll just wait a few minutes for everyone to join. And there's prizes for the first 3 people in the room. Like, so if you came first, second, third, if you're in the room, if someone's not, if you came fourth, you'll get it, etc. While I'm waiting for people to join, how's everyone going with assignment 2? Have we started? Okay. If you can get started on stage 1 as soon as possible, you don't even need to know linked lists yet properly for stage 1. You're doing mallocs. You'll be setting, I think, the linked list to null. So if that's what's stopping you because you don't feel confident enough with linked lists, just, have a go. Are we ready? Let's go. Yeah, it's not increasing. Okay, so this question said, what must exist in a linked list node? So a node has a pointer to the next, not a pointer to the head necessarily. Okay. Sorry if you're looking at this on a phone, it might be hard to read. People, at home. Okay. Yeah, yellow almost looks right, doesn't it? I was just then thinking, what was it? It doesn't actually have a variable. It's got struct, star node, and no variable. So we need... Actually, this is wrong too. They're all wrong.
Yeah. The pointer's supposed to be a 10, right?
All right, so what does that mean? I've always...
Make everyone correct. Communism.
Can I make everyone's correct? No. This is a Halloween special, right?
So there's trick.
No, I didn't mean that. I'm not going to pretend. Now, I think in this one I can review answers. So if there's ones that are close and it's just different spacing, oh, it doesn't have the underscore. Do we give it? No, it doesn't have the underscore. All right, I'm being tough, even though I got one, I had one that didn't have an answer. Okay, basically, yeah, new node, arrow data equals 99 with spaces or with semicolons or not. Okay. Now, hopefully everyone knows this. And hopefully I've got it right myself, right? Yay. So yeah, current equals current next. You're going to be writing a lot of that over the next few weeks. Yep, wow, very good. All right, so that's for all nodes. I keep looking at all the answers now, thinking, oh no, I hope they're right. Okay, well, one of them's right. Okay. Okay, let's have a look at what it was. So line 18 is fine. You can say current equals null. That's not going to cause it to crash. But line 19, if head's null, then current's null, and then you're doing null arrow next kind of thing. You're dereferencing a null pointer, or you're trying to access null. All right, is everyone clear on that? These are the sorts of things you're going to, yep.
But if it's already null, then wouldn't it just exit the while loop?
This is checking for current next to be null. So if you're checking for current, whether current's equal to null, that's fine. But if you're doing current next, which sometimes we are, that can crash it. And they're the situations where we need an extra case before it, saying if head is equal to null, do something special. All right. The last question. This one's not too bad. Yep. Awesome. So yeah, if you're just changing a value in a list, you shouldn't have to malloc. If you're just creating a variable like current to point to a node that already exists, you shouldn't be mallocing. All right. Let's see who won. Let us know if you're in here so we can give you your prize, which again, it's not that exciting, but you know. All right, so do we have Fabulous Deer? Fabulous Deer, are you here? Oh, cool. It's the skeleton one, the skeleton one. All right, well done. All right, Great Crane, are we here? Great Crane, okay. Great Crane's down here. And do we have, and well done, Great Crane. And Joyful Glider, are you in the room? Joyful Glider. Okay. They're online. Yep. Who came fourth or fifth? Fourth? Fifth? Did anyone come fourth? You came fourth? Did you come fourth? All right, you can get fourth and give fifth, just stuff from the bucket. Yeah, yeah. All right, well done, everybody. We've got a few minutes. We've got a few minutes to look at approach 2, which I know you all, can't wait to see this. So, this is another way you'll see it coded. I won't go through all the code for it today because we're not going to have time, but I'll go through the idea of it. It's going to have, when you try and code it up, it's going to have its own slightly different edge cases than what we saw with the other implementation, just for the nature of what we're doing. So in this example, we're just using current and we're moving current along, but we're always checking current next to see if that has the piece of data that we're looking for, which was suggested to us. So this is the while loop, while current next is not equal to null, and we're checking current next data, whether that's the search key. And then that's when we finish our loop. And we're doing current equals current next. So if we find it, current is going to be pointing, like when that loop finishes, if we found it, current will be pointing to the node before the one we want to delete. Again, we're just trying to connect this to here and delete this. Now, how are we going to do that in this situation? So if we free this first, if we say do free current next, if you can't read that, but free current next, then we can't access this next node anymore, right? If we free this first, we can't access this next node. But if I connect this up first, I can't access this node I want to free. I can say what?
Could you say current next?
You can say current next. You could say current next equals current next, but not if you free this first. And if you do that first and you connect this up, then you can't free this. So we're in that situation where we need another kind of variable to help us out. So we can just have temporary or something, however you want to do it, pointing to this node. So once we connect current, and yeah, you could say current next equals current next, or since I've got temporary, I could say current next equals temporary next. I've hooked it up, but I've still got to point it to the node that I want to free. Anyone see situations that might make this code crash or not work? Yeah, if temporary is null, what does that mean? But yeah, if temporary is null, this is a problem. Temporary could be null if we didn't find it. If we didn't find anything to delete, temporary might be null. We have to check for that. What else do we have to check for? What else could be null? Yeah, if current's null, this is going to crash. What about if we're trying to delete the first element? What's going to happen then? We're not ever checking the first element. We're checking current starts at the beginning. The first thing we check is the value with 17 in it. We never check 13. So we're going to need something for if the list is null, if we're deleting the first one in the list, and something special for if we didn't find it. Yep.
What is this searching?
Sorry?
What is this searching?
Oh, that just means the value we're searching for. So yeah, you'll see that sometimes in computing, search key, it's just what you're searching for. I've sometimes just called it value or whatever. So I'll leave that for you to have a go at coding up. We will go through the code next week. We're also going to extend I won't do it now because we'll be rushing through it and I'll make it even more confusing than it is. We're going to extend our first approach to delete all of the occurrences. So if we wanted to delete one and there were lots of ones, we'll delete all of them. So we'll do that at the beginning of the next lecture to just refresh and revise this. Give feedback as always. What did we learn today? Hopefully something. Next lecture, we're doing a larger linked list application. So everything we've done in lectures has been an array of integers. In the assignment, you'll be dealing with, just quickly for just 1 minute. In the assignment, you'll be dealing with all different types in your linked lists, not just one int. And your linked list won't just have one value either. The other thing is, these linked lists here are just linked lists on their own. In the assignment, your linked list might be a field within a struct. And for some people, that's going to add a whole layer of confusion. Well, for everybody, the first time you see that, it adds a whole layer of confusion. So we'll be looking at examples like that. Also with multiple files. Hopefully it will be helpful for assignment 2. So that's on Monday. After that, I'll get you to do a poll on Monday about whether we want the next lecture to be revision. Next week on Thursday, do we want it to be revision or something different that's non-examinable? I'll leave that to you to tell me on Monday. Some people will be thinking, I think most people want revision, but I don't know, I'm going to ask. All right, if you want some lollies, there are some left. Have a good day and see you on Monday.